Hello, Physics 2 students. In this video, I want to discuss Maxwell's equations. So thus far, we've sort of pieced out, the components of electricity and magnetism together through various kind of thought experiments and various considerations. And so that was done by people like Ampere and Heaviside and Faraday and other people. Um, Maxwell is the person who pulled together the whole consistent picture of what electricity and magnetism really is about. Or are. So what I want to do is kind of lead you through his thoughts. So we'll begin by writing the equations we have to date. So to date, we have Gauss's law for both either electric or magnetic fields. So for electric fields, we have the flux of the electric field through a surface. It has to be a closed surface. Gives you the charge inside over epsilon naught. And similarly for magnetic fields, the left-hand side looks the same. The right-hand side is 0 because we don't have any magnetic monopoles known. Then so those are both Gauss's laws for electric and magnetic fields. Then we have Faraday's law, which states that the line integral of the electric field around a loop equals minus the time rate of change of the magnetic flux through the loop, through the surface. And this is an open surface because it has to have a boundary given by the curve C. Finally, we have Ampere's law, which says that the line integral of the magnetic field around a closed loop equals mu naught times the current which pierces through that surface. All right, so this is to date what we have seen. And I'll go and tell you now there's a problem with one of these laws. So let's try to guess what the problem could be. To do this, we're going to simplify our life and go to empty space, go to a regime where there is no charge or current. Where the charge and current are just simply 0, out in deep space. In that case, we can write our equations as follows. Gauss's law for electric fields, Gauss's law for magnetic fields. Well, that looks nice in parallel, right? The same basic structural form to the equations. We have Faraday's law. Says that the line integral of E dot ds around a curve C equals minus d by dt of the magnetic flux through surface S. Nice. And then let's write down Ampere's law. This looks kind of weird. And several times through the semester, we've seen that there should be a sort of a parallel structure between electric and magnetic fields. These equations on the left are amenable to that, but the equations on the right are not parallel. We're missing something. We need something else other than zero here to kind of reinstate the symmetry. So if you want to, you could sort of argue by just sort of aesthetically, it would look a lot more parallel or look a lot more symmetric between electric and magnetic fields if on the right-hand side here, we want something like a derivative with respect to E dot dA, an electric flux. That's what, if we had something like that over here, an extra term, then the equations would have a nice parallel structure. Okay, Maxwell looked at these equations, saw that this parallel structure would be kind of more respected if such a term existed, and he figured out exactly how to include it. So we're going to start with Ampere's law, and we're going to see a problem. Okay, so we can determine this missing term by the following analysis. Imagine we have a wire carrying a current, and then there's a capacitor. And we're going to imagine that there is current I passing through this. So if you were, so this is a current carrying wire, so you would expect a magnetic field to wrap it. So you would expect field lines to kind of go like that. And we know from Ampere's law that you could draw an Amperian loop, which follows along. And then if you kind of drew the soap bubble, which subtends it, and they can have any shape here, there's no constraint. And we would simply say that the integral of B dot ds around the Amperian loop equals mu naught times the current, which pierces the loop, which is just I. That looks awesome. No problem. But we do have a problem. Let me redraw this, and I think you'll be able to see the issue. Remember, there really is no soap bubble. That's just a mental construct. So the same situation, same current, same everything, same magnetic field. We could draw the same Amperian loop. But, since the soap bubble or the surface was a mental construct, there's nothing preventing us from just extending it all the way over to this capacitor, on down, across, and over. So now we see the problem. The current is zero inside the capacitor. No charge actually crosses the capacitor. The charge accumulates on the ends of or on the plates of the capacitor. What the capacitor does have is an electric field, which is equivalent to an electric flux. So we're going to use the formula for a parallel plate capacitor to help us calculate this. Inside a capacitor, when I draw this loop or the surface here, the flux through the surface is simply going to be the electric field times the area of the plates, which is simply equal to the charge on the plate over A, epsilon naught, times the area, because Q over A is sigma. Canceling the A's, and I simply get Q over epsilon naught. So the flux, the electric flux through the surface is simply given by the charge on one plate, on the positive plate, over epsilon naught. This would be the electric flux. So basically what Maxwell did is he modified the right-hand side, and he said basically that Ampere's law should be generalized to say B dot ds around the closed loop equals mu naught I plus a new term with some coefficient C times d by dt on the electric flux. And we're going to use the following, the previous example, to figure out what the coefficient needs to be. So here's the situation. In this situation, I have no real electric field, and I just get the current contribution. But for the same Amperian loop, I could also route it through the capacitor, in which case I have an electric flux, and I can take its time derivative. And so I get that if I evaluate on one curve or the other, I should get the same left-hand side. So it must be that mu naught I equals C times d by dt on the electric flux. Which is Q or epsilon naught, otherwise known as C over epsilon naught times I. So evidently, C equals mu naught epsilon naught. If we choose this coefficient, mu naught times epsilon naught, then this generalized Ampere's law will always be true, whether we draw the surface crossing through the wire or the capacitor. So the new form, called the Ampere Maxwell law, says that the integral of B dot ds equals mu naught I plus mu naught epsilon naught times the electric flux. And we should take a partial derivative with respect to time. That's the new version, Maxwell. This is how Maxwell improved Ampere's law. And in doing so, he arrived at 4 equations which place electric and magnetic fields on symmetric footing. You might ask, well, hold on here. You can't just, I mean, we have experiments. All these things are based upon experiments. You can't just start adding new terms. Well, when you plug in and evaluate what this term is, this coefficient is approximately 1.1 times 10 to the negative 17 seconds squared per meter squared. That's this coefficient. So this term is tiny. It is, certainly with the tools of the 1800s, it is experimentally out of reach. So it's sort of a triumph of human ingenuity and just thought to see that this term must be present for the theory to be consistent. So on the next page here, I'm just going to write the 4 complete Maxwell's equations which describe the complete theory of electromagnetism. So, if this is a movie, there would be kind of a theme song with a crescendo right at this point, because this is a high point of human achievement, and it's a high point for the semester. It's the first time where we have pulled together in one place the full theory of electricity and magnetism in their full form. So we have Gauss's law for electric fields. Gauss's law for magnetic fields. We have Faraday's law, says that the integral and then we finally can write down the Ampere-Maxwell's law. So these equations describe the interaction between between electric and magnetic fields with each other and also with charges. To find the effect that the fields have back on the charges, we also have to include the Lorentz force law, which simply states Q E plus V cross V. And that's it. This is the complete theory and complete and consistent theory of electricity and magnetism. I've written them out as a set of coupled integral equations because that's the way we've discussed them all semester. These were kind of amazing because if you go back to the late 1700s or early 1800s, electricity and magnetism were just two separate phenomena. And with this unification, the two theories of electricity and magnetism were now unified into one theory of electromagnetism, and they satisfied these equations. All right. In the next video, I'm going to show how to rewrite these equations as differential equations rather than integral equations. This is a little bit, so it's sort of a new direction for our course, although most of you, if not all of you, have had differential equations and have seen differential equations. So it turns out that this differential equation way of writing Maxwell's equations, Maxwell's theory, are much more convenient for solving interesting problems, real world problems. Okay, so we will have that next.